set of lectures. This is meant to be an introduction to a relatively new approach to quantum foundations that's been pioneered by Rafael Sorkin and some of his co-workers like Faye Dowker. And we call it the quantum measure and co-event interpretation. The interpretation is based on, it's a histories-based approach to quantum foundations. And importantly, it does not require measuring devices, so it's observer independent. And that's the main motivation for looking for alternatives to the standard formulation of quantum mechanics. It is also a realist interpretation for those of you who have studied a little on quantum foundations, but it's not, in fact, a hidden variables approach. So let me just say a few words. So first of all, there will be 2 lectures on the quantum measure formulation. First by Rafael right now, where he will introduce it and flesh it out to some extent. Tomorrow morning at 10:30, please note the change in timing from the first message. I will continue 10:30 tomorrow morning. I will continue to the second part of quantum measure theory. Mostly I will review things that Rafael has already done, but also try to explain with examples. And at the end of these 2, we will have a talk by Deepankar Holmes, who will tell us about the general questions about the quantum measurement problem itself. Now, it would seem that his talk should come right at the beginning because we are talking about an approach that is measurement-independent approach. But the reason, in some sense, one justification for putting it at the end is that maybe when you look at these same questions that he will present to you, you will see them in a new light because you would have learned a little bit about this new approach, new way of thinking about quantum theory. And that will be tomorrow at 2 o'clock. So the format of these talks is to encourage discussions and questions. There's a lot of formalism in some sense, but there's a certain amount of climbing up, a sort of step function at some level. But on the other hand, because it's supposed to be something where you can ask questions, hopefully at the end of the day you go back with some kind of a coherent picture. Rafael did give a talk last year on the quantum measure approach, but one seminar was far from enough to introduce the set of very fairly complex ideas, complex at some level, but also very beautifully simple in others. So although they're free-flowing discussions and we encourage discussion, I'll also say that I'll be the sort of taskmaster here, sort of stopping things because we don't want it to go completely out of hand. And we will have today a discussion session, enough time for discussions after 4. So, yeah, after 4, during the talk, but if we just want to sit down, people want to sit down and have discussions, they can. Just an important clarification to make before these lectures begin is that the word quantum measure, and this seems to happen a lot, is that the word measure is often mistaken with the word measurement. And they're not related directly. Quantum measure is a generalization, a way to generalize from a probability measure in the measure theoretic sense. You know, when you do an integral, you have a measure in the integral. That's the same kind of measure. It has nothing to do with measurement. So I just want to tell Rafael to begin with.
Yes.
I think so. So Rafael, you don't need you just need Blackboard.
I want you.
Oh, you need
Just about.
There's a lot of mic.
So I need a mic. I don't know, can people hear? Well, you didn't use a mic. Everyone could hear you, right? You want a mic? Yes. Okay.
Or you could move to the front. That's another possibility.
Oh, but the camera needs a mic.
Oh, the camera needs a mic. Should The other lectures came out very nicely. So.
Oh, that's good.
Should I go?
It's the same in the chart. It's like on the others. Oh, this is great. So it moves. It doesn't equip, it's not picking up with another. Yeah, is this working? Higher up?
Breathe higher.
Higher up. Where's that thing going?
And it's sleeping down.
Oh, it fell down. Yeah. I'm just afraid it'll fall because it's not. The spring is too. I have to put it through my button.
The mic is falling down.
Yeah, the clip is not strong enough. How's that? Is the
Loud
volume,
enough?
is that loud enough?
Yeah.
Louder? Okay. Okay, so I'm feeling a little bit schizophrenic here, so I've given two lectures on entanglement entropy, then there'll be this, then on Thursday, 2 more lectures on entanglement entropy, Thursday and Friday, and now it seems that tomorrow maybe I'll be talking to the astronomers on cosmological constants together with Sam. So I have to sort of steer my mind from one topic to the other. And today also is a little bit schizophrenic in the sense that there's no simple, I have sort of 3 goals, because it's not just a question of interpretation, and it's not just a question of formalism, it's really a question of both. So to do properly, really, an exposition of what I'll be talking about would not in any way fit into just this one session. So instead what I'm going to try to do is at least give you a feeling for what I would call a histories-based approach to thinking about quantum mechanics. And that has different aspects. And so what I want to say will be sort of in 3 parts. The first is at the level of formalism and mathematical framework. What is histories-based what do I mean by histories-based quantum mechanics? When you say histories here, you should understand the word in the same way that it's used in the phrase sum over histories. In other words, it's a reference to a path integral kind of way of thinking about quantum mechanics. But where path integral should not be viewed merely as a technique for solving the Schrödinger equation, but as actually a self-contained formulation of quantum theory. And going along with that is what Sumati mentioned, the histories-based quantum mechanics and the quantum measure. And she said measure is to be understood in the sense of integral, like in path integral. That's unfortunately the in mathematics measure theory exists and is a generalization of probability theory, but the word measurement is something different, although they're of course related in the context of quantum dynamics. The second thing, since this framework is different from the one that most people are used to, although I hope that most people are also to some extent familiar with this framework already, but the standard framework, which is based on ideas like Hilbert space, operator, projection operator, collapse of the wave function, measurement, all that framework is sufficiently different that it's possible that this more general framework could lead to actually non-trivial generalizations of quantum mechanics. And so I want to, especially because Urvashi, I thought was going to be here, but is not, has done some experiments testing for whether one of his generalizations is required by experimental results. So there's two ways in which one could in which this histories framework leads beyond ordinary quantum mechanics and could predict new effects. I mean, could accommodate new effects, new types of interferences, I would say, that cannot be found in ordinary quantum mechanics. And I'll mention both of them. One is more radical and one is less radical. I just want to give us a sense. There's no definite, unfortunately, I won't be able to give a definite experiment except for the one that's already been done and is being, I think Urvashi is setting it up again here, so if you might like to visit the lab and see the apparatus that she's using. But that one has already been done and is being improved. And set bounds on violations of quantum mechanics. They're being improved, but in principle there could be other kinds of places one could look for post-quantum behavior. But at the moment I'll just indicate at a sort of abstract level, general level, the kind of thing that one might expect without proposing a specific experiment, like the three-slit experiment that Urvashi did. And then the third thing, get to the more philosophical or more conceptual interpretational aspects which Sumati referred to, and I'll call that co-events. We refer to this kind of interpretation using the word co-event, which I'll explain, and the particular, as I'll say in more detail later, this co-event kind of formulation admits of different variants, and it's a sign of the immaturity of the whole approach still, that we don't know which is the best variant within it. So, however, there's a simplest one, and there's one which is easiest to explain. We call that the multiplicative scheme. And I'll introduce the co-event idea in connection with that scheme. So was there a question? So as I said, I try and give you a feeling for these things. What I would hope is that you will feel after this, if you think about it, you'll feel more comfortable with a kind of history's way of thinking about quantum mechanics, and have a sense of the kind of thinking that it involves and how it fits in naturally to this particular interpretation or formulation of quantum mechanics. So let me start with the first point, histories, first topic. What do I mean by histories-based quantum mechanics and what is the quantum measure. I never know whether to call it there's two adjectives for quantum mechanics. One is quantum, and the other is quantal. So I never know which one to use. You can call it the quantum measure, or the quantum measure. This quantal seems to be more in use in European context, by European writers, French writers especially. So let me start by asking a question that I think Orpus, you might remember my asking people when I first went to Institute for Quantum Computing in Waterloo and talked on this when they were just thinking about doing the three-slit experiment. So let me ask your opinion, from people in the audience. What do you think? What is quantum mechanics about, and what is it that makes it different from classical mechanics? Depending on how you answer these things, you'll be led, you're thinking in what I would call the histories-based way, or you're thinking more in the other way, which I don't have a clear, simple name for, but let's call it the Hilbert space operator way of thinking about quantum mechanics. So I'm going to make a list. So let me ask, what is quantum mechanics about? And why does it differ? You know, what's characteristic about it from classical mechanics? So actually the question, what is it about, might be a little vague, but if it sounds too vague, I'll try and suggest possible answers, but let me for now leave it completely open.
You're asking us?
I'm asking you. Anyone? Yeah, I'm hoping for many answers.
I would say that classical, on the mathematical side, classical physics is based on a commutative algebra of observables, and it's a probability theory on a commutative algebra, and quantum physics is a probability theory on a non-commutative algebra. That's it. Rest follows.
That's the whole story.
From there it follows everything else.
Okay, so that's
space-time, and algebra could be algebra of functions on a space-time, defined on space-time regions, whatever. Okay? Or it could be spin or whatever it is. Okay? I would claim this is it.
Okay. I would say the physical difference is that classical mechanics claims to be a deterministic theory.
okay.
And quantum mechanics gives up that determinism and only tries to.
It follows from this.
Yes, but
But it is a more physical content. And I
Then
think
everything else is deductive. This is the grand thing. Then everything else.
but maybe you should.
physically, why would be it commutative and non-commutative, and why quantum mechanics should be non-commutative?
Should be, I do not know. I don't know
But
why
it turns out to be.
it is how nature seems to be.
So what, any
What's that?
others? Sadik?
It's just something which measures. I mean, it's the way you make sense of the results of measurements when things are small. I mean, it's for me, quantum mechanics, the way it is structured is a fixed up theory, which I mean does not have a. I mean, it's sort of designed to give answers, but it doesn't give you the methodology. I mean, it doesn't give you a framework. I mean, there's a mathematical framework, of course, which underlies this, but it's more. If a nice mathematical framework didn't give you the answers, you would reject it, and you would pick up the mathematical framework which gives you the answers. So I have sort of a sneaking suspicion that a lot of the founders of quantum mechanics as we know them today were actually engineers by training, and they used that to good effect to get the answers.
So how would you compare it with classical theory?
Oh, essentially in classical theory you have you can describe the system in phase space without any ambiguity. Okay, in quantum physics, I mean, it allows you all the known variables to specify all the known variables, whereas quantum mechanics does not, and it goes back to the non-commutative nature of this thing where the H cross comes in and your phase space volume is essentially limited.
Yeah, Purva would like to also.
I want to add a
I
different
just want to make a
ingredient.
little less than, yeah.
complex numbers.
Complex numbers, right. Versus real numbers.
Microscopic versus macroscopic.
Micro versus.
And Urvashi, you wanted to say something?
No, I was going to say that this probabilistic versus deterministic is what I
So this is what it's about. You're saying it's about the microscopic world, whereas classical mechanics.
I wouldn't say versus. When we go,
Oh, you mean?
when we probe the quantum classical background boundary, we are sort of pushing the limits between the microscopic and the macroscopic.
But I would be happy if I can start from Sam's argument and reach Dipankar's argument, and then everything follows from there.
Balzer.
Balzer about the
So can we go like this? Can we get your argument from his argument?
Yeah,
By the way, I want to make one
I
remark.
don't want to have a long, discussion. I
Just
just
to
want to
get,
get it.
like, what about the
involve the most-
students?
Yeah.
It's a kind of an important thing to students, like when you first encounter quantum theory, what is it?
I'm sure, JK, you have an opinion about this.
Entanglement, yes. Okay, so some of these are in my list, some of them were not. But let me sort of put them sort of in two columns, one of which represents what I was calling the more traditional approach, and one more corresponds to the histories-based approach, and then see what people think about this. So when I said, what is it about? Some people might say it's about the wave function and how it evolves. Some people might say I guess this would fit more with what Ball introduced. It's more about operators or
And states.
Operators and states.
Wave functions are all
Well, but
may be emergent.
just operators, an algebra, and the answer, see, the one that I would give is that what it's about is the same sort of things that classical physics is about, which are called which we call, or people have called histories. So an example of a history, I'll give you an illustration in a little bit, but if you want to think of a simple, have a simple model in mind, it would be, if you're dealing with a system just comprised of a few particles, the history would be a world line for each particle. In other words, what would count as a classical reality if you were doing classical physics. And it's the object that goes into the sum over histories of the past interval. So that's what I mean by history. That's a crucial concept, of course, for histories-based interpretations or formulations. So I'll try and flesh it out a little bit more, but I hope the basic idea is already clear. So for example, if you're doing electromagnetism, then a history would be an electromagnetic field, but it's an electromagnetic field on all of space-time, not just on space at a moment of time. If you imagine doing gravity, the history would be a foreign geometry, and so on. So what it is depends on the exact field of study. If we had the full standard model of everything, then the history would be, we would know exactly what kind of object the history is. But that's the task of physics to reveal to us, which it is solely doing historically, in the other sense of history. But of course, we don't yet know the full story, but we know a lot of things that are histories and that describe a large part of nature. Okay, so that's what I mean. So I think the most traditional answer, for example, there's a philosopher of physics called a physicist, but who worked a lot on what I often like to mention in this setting called Mitsuo Taketani, a Japanese writer on philosophy of physics, and he has a whole book on the interpretation of quantum mechanics. I think I learned a lot from his way of thinking, but when it came to quantum mechanics, he said, if I'm remembering right, that what it's really about is ultimately the wave function, the state vector, if you like. That's one view, but it's not really compatible. It's sort of at the opposite pole of the view that I'm going to be promoting here. Another question is is it about momentary states, or is it about what you might call processes, which really means things that take place in time that are not described just by a point in space or something like that at one moment of time. Again, the more traditional view, you might say, is that it's about momentary states and how they evolve. You may, in a Heisenberg picture, it may look like the operators are evolving, and the state evolves only in this discontinuous way when you make a measurement. But if we think, again, at this extreme opposite pole, you think of the wave function and how it evolves in time. That's the Schrödinger equation. That would be the essence. Think of processes, it's different. It's something extended in both time and space. Is it about measurements? Not in the sense of measurement with apparatus, or hopefully some of this term will become comprehensible as technical terms, event. So the word event is has a technical meaning which I'll describe. It's a set of histories. But here I'm using it in a somewhat looser sense. It's compatible with that, but not, I don't mean to make it so technical. Something that happens in the real world as opposed to something that gives an output in our laboratory. So this histories formulation wants to be about the real world and not just about the output of our instruments. So I rather say events. And then, in what sense is quantum mechanics a development or generalization of classical mechanics? What classical theories are most like it and can give us inspiration for the right formulation of quantum mechanics? I think the view that you usually learn, and which probably is fairly historically accurate, is that it's a generalization of Hamiltonian, quantum mechanics is a generalization of Hamiltonian mechanics. But the other view is that this is related. Hamiltonian mechanics is, of course, a deterministic theory. And one of the answers that people gave about quantum mechanics being different is that it's non-deterministic. So there are classical theories of non-deterministic systems, non-deterministic dynamics, and that's called, the technical term as it's used in mathematics is stochastic process.
Statistical mechanics?
And statistical mechanics. Statistical mechanics is very much part of this, although a lot of, in the way it's actually worked out, until recently anyway, a lot of statistical mechanics was basically equilibrium statistical mechanics.
But the non-equilibrium part is non-deterministic also.
That's right. It's non-deterministic. No, it's crucially, part of it. Although in the classical statistical mechanics, it's non-deterministic, strictly speaking, only because there's some randomization over initial conditions. Once you set the initial conditions, then everything evolves deterministically, if you had access to the full microscopic variable. But of course, if you coarse grain, that is, you give yourself access only to some average properties, or you can only observe certain particles, then they appear to behave in a non-deterministic way.
On the other hand,
So,
if you bring in non-equilibrium stack, because of friction, for instance, then in irreversibility.
Well, okay, so irreversibility is not exactly the same as indeterminism, although they're certainly related. Because something like the heat equation is a deterministic equation. If you set up a heat distribution of heat at some moment of time and let it diffuse and so on, it'll of course even out, at least until it comes to a uniform temperature, at least non-relativistically. But that's a deterministic process. So if you know the distribution of the heat at the energy density at some moment of time, then it's completely determined.
It is the noises.
But it's not. But it's very far from reversible. Well, So right. So it's the fluctuations that go beyond that that are truly
distribution is
indeterministic.
connected to fluctuations and through the fluctuation.
And they're related. They're related, right? So you can't really have one without the other, right? So, but there's a mathematical theory of things which are non-deterministic. And you don't even need to presuppose that underlying it is some deterministic evolution, like there is in classical statistical mechanics.